All right, welcome to one of your last lecture videos. So today we're going to be covering theoretical and percent yield. So let's go over what theoretical yield means in chemistry. So it's essentially the amount of product in which you calculated that you should maximally obtain. So like, for example, if I calculated using stoichiometry that I should produce 0.27 grams of O2 gas. That is my theoretical yield. That is the maximum amount of oxygen gas that I can get out of this reaction. And of course, I do this by using our stoichiometry methods in which we learned so far already. So we'd go from grams to moles, moles to moles, and then moles back into grams. However, actual yield is different. So there's theoretical yield and then there's actual yield. Actual yield is different in that it's the amount of product you produce experimentally. In other words, you cannot find the actual yield yourself unless you actually run a full experiment with it through. You're never going to end up calculating actual yield. You're only going to be measuring exactly how much of whatever you produce. This is a skill that like a lot of pre-meds, biochem majors will have to master, as you'll constantly be finding theoretical yield in years to come. So this is an essential skill that will not leave you anytime soon if any of these areas interest you whatsoever. So how do we calculate percent yield of a reaction? So remember that percent yield is found using your theoretical and actual yield. Actual yield will always be given to you if necessary, right? So this is the formula that you definitely should have written down, or maybe on your note card too for this upcoming exam. Percent yield is equal to actual yield over theoretical yield times 100%, right? And we do the times 100 piece just to make it into a percentage so that we're not just looking at a decimal, even though technically a percent is a decimal, but so what's the purpose of determining percent yield? Right, so it's incredibly important in determining how effective reactions are. Typically, a yield of just 50% or higher is pretty good in chemistry. However, it entirely depends on the type of reaction you're using. Some reactions are naturally just going to be more favorable than others due to things like thermodynamics and like the way that molecules arrange themselves in space and time. That part's not too important for this course. You'll learn more about that more in like general chemistry 1 and 2, but often in organic chemistry, for example, it is difficult to obtain a high yield, and it's often due to the way that they arrange themselves, right? Like I said, and they interact with one another. So generally what you calculate, what you should get is often not going to be what you get. In fact, I don't think you might earn a Nobel Prize if you can run a reaction to 100% completion, just because it's that difficult. So just to go over this a little bit, we're going to go ahead and run through an example. So consider the following reaction. So we have iron 3 oxide reacting with 3 solid carbon to make 4 solid iron and 3 carbon dioxide. A chemist runs the reaction using 28.4 grams of iron 3 oxide, and excess carbon. So these are important pieces. I'm just going to underline them. They obtain a yield of 10.2 grams of iron. What's the percent yield of iron in this reaction? So we know that our percent yield is equal to actual over theoretical, right? And then times 100%. So they give us the actual yield. We just need to find theoretical because we don't know how much we should be getting as of right now, right? So in order to do this, right, we use our stoichiometry. So we start off with 28.4 grams iron oxide. iron 3 oxide, should I say. And we need to get this value into moles. So, sorry, just grabbing my periodic table real quick. So we have 2 irons, 2 times, and we also have 3 oxygens. So for every mole of iron oxide, there is 159.86 grams of iron oxide. I'll just leave it like that for now. Okay, so now we're no longer in grams, we're in moles of iron oxide. So now we need to get into moles of iron. And we're going to use our molar ratios in this case to do that. So we know that for every 2 moles of iron oxide, 4 moles of iron are produced. And then our last piece here, right? So we're no longer in moles of iron oxide, we're in moles of iron. We just need to figure out how many grams of iron we produce now. And we know that for every 1 mole of iron, looking at our periodic table, 55.938 grams of iron are produced. So when we do this calculation, 28.4 plus, oh, I'm sorry, divided by 159.86. And I get a yield of 19.87, sorry, I didn't need to put this little dot here. 19.88 grams of iron has been produced, right? And seeing that we can only use 3 sig figs, we're going to go ahead and round this to 19.9 grams of iron. And this is our theoretical yield. So all we need to do is plug this value into here. And then we should be able to obtain the percent yield. And seeing that we did all the calculations correctly, we should be able to obtain a yield of 51.4%, or something really close to that. And then a key thing about these calculations is do not round intermediate calculations. So only save the sig fig portion for the very end. Keep track of sig figs as you're going along with these calculations, but do not round any intermediates, or else you might get an incorrect answer, or you're going to start getting answers in which are not useful. Okay, and here's a second practice problem that you can do if you have free time. Feel free to pause it here if you would like to run through this, and then I'm going to show the answers now. So nitrogen was the limiting reagent, and you should have gotten a percent yield of the reaction of 80.6%. And some general tips I would like to give about finding theoretical and percent yields in general is that actual yield is always going to be less than your theoretical, unless you did something completely wrong. If your actual yield is bigger than your theoretical, let's say in a laboratory setting, for example, like let's say you obtain a yield that's greater than what you should have obtained, it's very likely that your product is contaminated and there's other things in it. But like in terms of this class, if you obtain an actual yield, or like you somehow get an actual yield that's bigger than your theoretical yield, you probably miscalculated your theoretical. And then we've already practiced stoichiometry a lot in class, right? So that part you should be more or less familiar with by now. If you're not, I highly recommend you start getting that stuff down. And familiarize yourself with implementing the ideas of theoretical and actual yields and how to calculate percent yields with them. So for the final that's coming up, you might get asked a question that's a little bit of a combination of stoichiometric things that we learned about, right? So you might have a problem that not only asks you to identify the limiting reagent, but it might ask you to find percent yield in addition to that. So just be comfortable with all the stoichiometric ideas that we have covered. You have the previous example in which I gave you guys, which is kind of a mix of both, and how like questions like that might be asked in an exam. However, if you want additional help, I recommend this to my section, but also I'm sure this can apply to other sections, is that thoughtco.com is a very, very solid website for general chemistry. If you just Google ThoughtCo and then space whatever you're learning, so like ThoughtCo limiting reagents, you can go to their page and they have a lot of useful examples and walkthroughs on these type of problems. So if you need additional practice, I highly recommend checking out that website. But yeah, all right, that should be it for this lecture. All right, have a good one.